Okay. Hello, hello. Zach, congrats on the first. And so yeah, today we're going to be doing a little like special thing where Slim will be showing me about number theory and trying to convince me that it's cool because I've always hated it. And yeah, and then we'll probably do math help afterwards. So hi, Slim.
Hi, Don. How's your day going?
It's going well. Uh, Nothing too special. How about you?
Pretty good. Do you know about Pando?
Pando?
Yeah.
I don't think so.
So, I mean, you live in California, right?
Mm-hmm.
So, what is the name of that giant tree in California? The giant sequoia?
Oh, like redwoods?
Yeah, well, there are several parks, national parks that have them, but I think that the type of tree is like a giant sequoia. I'm not sure. Have you been to those parks?
Yeah, there's a whole like map of them. There's one that's not too far.
Oh, nice. And have you hugged one of those trees?
uh, I probably did as a kid. It's probably a picture someone if I dug hard enough.
I mean, they are pretty big. I don't think you would be able to embrace them completely, right?
No, no.
Well,
There's definitely one that you can go like underneath because the roots are so giant.
oh yeah, yeah. They built like they make the tree into like a bridge or kind of like a crossover, right?
Something like that, yeah.
Yeah, so you can actually, I think you can drive a car into the tree, and
Oh, I don't think I've
yeah,
seen
it's
that
like
one
a
then.
yeah. But yeah, so yesterday I was looking at the biggest live organisms, and I always thought that those three were the biggest ones, but and they're pretty big and they're pretty old. Like some of them, they estimate that the age is like 2,000 years. But there is Pando. Like there is anything else in Earth and Pando. And Pando is this type of tree that grows from the roots. And when you look at Pando, it kind of looks like a forest. It looks like a bunch of individual trees, but in reality, it's just one giant tree. So yeah, that's
Huh.
Pando. And yeah, like all of these ones, like the all of those things that kind of look like trees, there is only one tree, and all of them have like the same root, and they share like it's just like a giant organism. Is massive.
Oh, yeah, I've never heard in general like forests have like a fungus like network in their roots. But this is literally
It,
like one giant tree.
it's just one. Yeah, same genetic material. Like they've done genetic analysis on it. All of it is exactly the same. It's been alive. They estimate for 15,000 years. So yeah, I had no idea. It's pretty fascinating.
Wow.
Yeah. I'm not sure how it is related to math. Maybe it is. Yeah, like I guess it's related to number theory. That's my way of introducing the number one. That's just one organism.
There we go. Yeah.
Yeah. Uh, but yeah, no, like, well, anyways, yeah, let's start with the math because people probably want to that. But so let me know why don't you like number theory? What are your feelings about it? Or
Uh, it just it just feels so restrictive to only be able to deal with natural numbers. I guess is my biggest thing. And there's a lot of
yeah,
things
it's very.
where it just doesn't feel
Go ahead.
very helpful. It sometimes it is helpful, but it's kind of it feels like kind of iffy.
Well, I think you're right on both accounts. It's very restrictive, and that's one of the reasons that makes it difficult. But on like, and it's also true that in general, the applications are not necessarily obvious, and it's definitely a field that historically has been not based on applications too much, more based on like curiosity, I guess.
Hmm.
But recently, like due to the rise of computers, I think that the more applications are coming along. And I thought about it, and I thought that maybe something that would attract you to number theory would be to learn RSA and at least encryption algorithms. But I'm not sure. I didn't prepare that because maybe you already know it. Do you know anything about that?
Ooh,
The
yeah, I've
encryption
been
algorithms?
introduced to it. It's been a minute though. I know he's
Yeah.
primes and like modular arithmetic, from what I remember.
Exactly. So I think that's probably one of the biggest applications nowadays. So I'll try my best and try to show you some interesting things or try to give you a sense of some interesting problems. It's definitely more restrictive, but if you think about it, natural numbers are the first type of numbers that any person would come up with, and it's interesting precisely to see how we have how, how the concept of number has evolved with time. Like for a long time, natural numbers were the only things that were accepted, and then the introduction of negative numbers was not that trivial. And then you have rational numbers, and people didn't like irrational numbers. And now we are pretty much comfortable with complex numbers, and that were not accepted that much also. So it's kind of interesting to trace back the history of this and see where it all starts with this with natural numbers. So what I did is I selected a few problems. Let me find them, and then I can share them with you, mm, and then maybe we try to solve them, and maybe that will motivate you. Because one thing that I've noticed is that you enjoy solving problems, and at least during the streams, you enjoy solving them once and learning like new techniques. So I thought that maybe that would help you, or that would make you more interested in learning this.
Okay,
What
sure.
do you think?
Yeah.
Okay, so before starting with, well, I'm gonna show you the first problem, and you can tell me if you know it about it or not. But basically, just so you get a, I mean, and obviously not. I mean, I'm starting very basic, so maybe all of this is pretty basic to you. I don't know. But before we solve it, I kind of wanna give more motivation to the problem, right?
Okay.
Okay, so I just put it. Can I move things around with this?
Yeah, with like the
Yeah.
little cursor. Yeah.
Yeah, okay. So, okay, but I have to actually see how it looks on the, okay, yeah.
And I can like zoom out
On
and
the,
stuff too to
no, it's fine.
help.
I think
Okay.
it looks, that looks well.
Yeah,
Okay.
I think so.
Okay, actually too small.
Uh, I think it's fine. Like,
All right.
I think
All
it'll be
right.
readable.
All right. So here the first problem is use the Euclidean algorithm to find the greatest common divisor of 93 and 42. And this is kind of like the thing that you wouldn't do by hand, but for this, I'll ask you to be patient, and I
Oh
have a
yeah.
plan or a reason to make it by hand. Normally, you would probably use a computer for this, but the first observation that I have is that when we think of numbers, before, I mean, maybe you already know how to solve this, but just kind of like to get a sense of it, right? So, I mean, let's say that our natural numbers start at 1. I don't want to start any crazy discussions here. I wonder why my pen is so thick.
um,
I don't know.
it if you like, there's a stroke width. Oh wait, no, you're probably on the thinnest already. I guess it's just a zooming thing.
Yeah. Oh, and why does it look black instead of white?
Oh,
That's
I did
weird.
make the background dark. You can make it white if you click on the big color box on the right.
Oh, I see.
There's
So the
like,
thing is that
yeah,
they have a dark mode. I'm on dark mode, so the
yeah.
background is transparent, right? But I think that your background is actually black. I
Oh, we
think I
don't see
think
the
it's better.
same one? That's crazy.
Yeah, I don't think we see the same one.
Okay, I can
Um, let
make
me
mine
see
white
because
to match.
like if you go to the hamburger thing, is it there? No, maybe not
There's a
there.
canvas background on there. I thought I'd change it for everyone. Oh, I see the dark theme. Oh,
Yeah,
wow.
exactly. There is a difference between having the, yeah, like if you use dark theme, it actually
Interesting.
changes everything. Yeah.
Okay.
Now it's dark. Yeah, now you see it's white. Okay, so now we see the same. That's nice. So you usually picture numbers like this, right? Because I mean, especially if you're used to the real numbers, you probably have a line for the real numbers, right?
Yeah.
And this representation, I mean, I'm really huge on visual representations, and this representation tells you something but doesn't tell you too much. It just tells you like, okay, 2 is the successor of 1, 2, like it gives you like the order, but not too much besides the order. And it turns out that in number theory, like that order is not as important as the multiplicative structure.
Hmm.
And when you think about the multiplicative structure of this, or how things multiply, it's usually a better representation, and not that you're going to draw it in the same way that you don't draw the real line all the time. Like it's just kind of like a good picture to have in mind. A good representation from the, this is not the pen, this is the line tool. A good representation to have in mind is to represent the structure is, okay, you start with 1, right? And then you to write 2, you write 2 on top because you can divide 2 by 1, right? Then 3, you can also divide by 1, so you write it here. But 4, you wouldn't write it here, you wouldn't write it here on top because 4, you can divide it by 2, right? And
Okay.
then you got 5, right? And then you got 6, but 6 is 2 times 3, right? So 6 would lie here. And then 7 lies here, 8 would lie here, and so forth and so on. Like 9 is 3 squared, so 9 would lie here. 10 is 5 times 2, and now it gets a little icky because I need to cross things here. 11, again, is here. 12 is 6 times 2, right? So 12 would be something like here. The parents would be like 6 and 2. 12, 13. I want to get at least to 15. So 7, 14 is something like here, right? 7 and 2. And 15, which is 3 and 5, right? Maybe 15. I'm going to write it here. I mean, it's not ideal, but you get the idea, right? Does this representation make sense?
Yeah, I can imagine that like the powers of primes will just be straight lines up.
Yeah.
And yeah.
And which ones are here? Which ones are in the first row?
The powers of 2.
No,
Or,
like I mean,
the first row.
look,
I'm sorry, primes. I was thinking of columns.
yeah. So these ones are all the primes, right? And then you kind of start building them up, right? So this is a good representation. And an interesting thing that happens with this representation is that if you have two numbers, let me change the color. For example, I don't know, 12 and 15, right? Then you can trace the first common parent that these two numbers have, right? So in this case, the first common parent that they would have is 3. Does that make sense?
Yeah.
And what is the name of this common parent?
Greatest common divisor?
It's the greatest common divisor, right? Because all the parents of elements, when you represent them this way, they are divisors, right? And then the common parent is the common divisor, right? And obviously 1 is also a common divisor, but is smaller than 3, or is in a different level than 3, so or on a lower level than 3, so you stay with 3, right? And you can do also the same going up, like if you go up at some point, well, this will keep growing, but at some point 12 and 15 are gonna meet here at some point. At what number would they meet?
60.
60. Yeah, I think so, right? So 60 is a divisor of 15, and it's also a divisor of 12, and I think it's the smallest of those, right? Like anything smaller than 60 wouldn't satisfy both conditions, would it?
No, you're only actually
Okay.
30 and 45, right? So
Yeah, and then this is the MCM, right? How do you call it in English, by the way?
least common multiple.
Least common, so it's LMC, right? So yeah, so that's my bad. Yeah, I guess I'm more. I'm not that used to the English, some of the English words.
No worries.
Which one is the eraser? Okay,
yeah.
Okay. Oh no, I also erased the problem.
You can control the undo. Yeah.
Yeah, control C, I guess.
You can also select it and hit delete key.
Yeah. I guess you have to kind of. Okay. All right. So okay. So yeah. So this is kind of like the structure that we want to keep in mind, and we'll start trying to figure out fast ways of finding this greatest common divisor. And as we will probably, I don't know, you probably already know that with that one you can also get, like, once you have this one, you can get the other one.
There's a formula. Yeah.
Yeah, there is like a formula for that. All right. So do you remember the Euclidean algorithm?
I'm pretty sure. Yeah, you do the kind of like long division until you get a remainder of 1. I want to say, or a multiple of 1.
Yes, basically. I want to erase everything without erasing the problem, which is now being challenging for some reason.
You can like click and drag a box and then hit delete. Yeah.
Okay.
You probably need to move the problem out of the way for the top stuff. Or that
Okay.
works.
All right. So, so can you solve this problem then?
Sure.
Okay, let's try to solve it and see how you do it.
So, if I'm a, oh, am I on black? Oh my gosh, why is it so laggy?
Yeah, I think you have to look at the Scully draw. Are you looking at the Scully draw or at the Twitch?
I'm looking at Scala.
Oh, that's weird. Yeah, sometimes that happens to me. That's why I don't like Scully draw. I don't know. I feel that it happens when I drag pictures. I feel that that's the reason why it happens. So I wonder if the reason is because I drag the picture instead of you dragging the picture.
Maybe. It's just weird how it's
Oh.
never done this to me before.
Okay, so let's erase everything. Let's erase the picture and see if that helps. Like if I erase this picture here, is now better?
Just the entire thing is being super slow. That's so
I
annoying.
wonder.
Maybe I need to refresh it. I hope it doesn't.
Yeah, let's refresh it.
It might make us lose our session.
That's all right. Yeah,
Huh.
this happens to me. I thought it was just me, but now I wonder why it happens.
Yeah, maybe I'll close out of my browser entirely.
All right.
And then just reopen it.
All right. Alrighty. There are actually things there. Is it better?
No, that's so annoying.
Do you want to start like maybe at a different Scully draw session? I will get out and then you'll send me another
Yeah.
link and see. Yeah, because it's working like that is super hard. On the other hand, if you want to just solve it on
Oh, just like on my
journal,
stream? Yeah.
yeah, on journal, that's also fine. And the only annoying thing is that if I want to say something, and I don't know if you need to change layups if you change that. So I don't know.
Should just be quick. Also, even when I'm not in a session, Excalibur is very laggy.
Yeah, I don't know why. Yeah,
Do I have that one process running? Huh. Okay, yeah, that's my bad. I've never had this issue before.
No, it's just, yeah, I guess it's just a Scully draw being annoying.
So I'll still make another link just if it's easier
Just to
to
see
for
if
you to
it
show
works.
things, but I might need to work separately.
Yeah, that's fine. I mean, I sent all the little problems uh, on Discord, so
Oh, okay.
you can open them there and just drag them there, I guess. Yeah. All right. I
Open
opened
that
the
up.
Scully draw. Is it still bad for you, the Scully draw? Just
Uh,
to,
Let me
I
try it.
guess, worth to check.
Yeah, it's still very
Yeah,
laggy.
so that's fine. Then just, yeah, I'll write on a Scully draw, and then if I want to tell you something, and then you can do it on your side.
Okay.
Um, yeah, it's probably better because I feel that like sometimes when I talk math, I end up like just doing everything and not letting people do things. Yeah. So yeah, so I think it's better this way.
Okay, I'm just bringing in the
It's
first problem.
it's destiny.
Yeah. Okay,
Okay.
so we set up like 93 equals 42 times something plus the remainder, from what I remember.
Yes. Yeah.
So probably 42 times 2 is
It's
84.
84, right?
And so then we have 9 left over. And then I think you do like a shift, like the 42 goes on the left is equal to 9 times something. Okay. And so that'll be times 4 plus 6.
Okay.
And then you shift again. That'll be 1 times 6 plus 3. And I think because we're multiplying by 1, that's when we stop.
Yeah, I mean, you can no multiplication by 1 doesn't make it a stop. It just stops. What happened if you try it again?
Oh, I guess, yeah, we'll get 0 remainder.
Yeah, like I mean, it's easy to remember just to do it up to 0. But again, this is the kind of thing that you probably wouldn't do manually anyways. Okay, so let me like if you can share my screen and then I'll unfortunately I guess I'll have to redo the things that you did. Well,
I could paste a screenshot on if you wanted it.
yeah, why not?
Okay.
Yeah, why not? Yeah, I wonder why like the two annoying things is that it's so thick. So thick. I guess if I make it smaller like this, it would look kind of normal, yeah. All right. Okay. So
It's dark mode that does it. What?
oh, you think so?
Yeah, I just switched to light mode and it's fine now.
I guess did you need to have a dark soul for it to work?
Apparently.
You're too
Oh, that's
too
wild.
much
Okay, so we
light.
can keep using Excalibur then. I'll just be in light mode.
Oh, okay. That's interesting because I'm using dark mode, so I don't know. That's pretty weird. Okay, so one thing. So first, why does this work, right? So a common notation for the greatest common divisor is to write this like this, 9342. This number. I know it's confusing because it kind of looks like an interval, right? But this is kind of common. If you want, you can write GC whatever at the beginning. But this notation is common. So okay. So it's okay if I use it.
Yeah.
Okay, so what's happening in the algorithm is that this thing it's equal to 42.9. It's equal to 9.6, and this is equal to 6.3, and this is equal to 3. Like, and when we use the notation with just one number, it just means multiples of 3, kind of. But
Okay.
anyways, let's not get lost there. And the reason why this works is because in general, if you have A, B, this is the same. You can do this, assuming, well, let's assume A is smaller than B. Yeah. So you can subtract the numbers, and it's not easy. It's not hard to see that this is true because anything that is a divisor of A and a divisor of B, it's also a divisor of A. Well, it was to start a divisor of A, but it's also a divisor of B minus A, right? Like for example, in this case, whatever thing is a divisor of 93 and 42, right? I mean, this is not. I mean,
Oh,
I'm
it's like a
going a little bit.
modular arithmetic like type of idea.
Yeah. So yeah, like whatever is a divisor of these two. Well, we already know that the common divisor is 3, right? Like 3 divides these two of them, the two of them, right? But then it also divides 42, you know, because 42 is one of them. So obviously, if it's a divisor of these two, it's also a divisor of 42. But the claim is that it's also a divisor of 93 minus 42. What is 93 minus 42?
51?
51. And you see, indeed, 51 is a divisor of 3. So this is always true.
Okay.
That's that. And now, instead of subtracting 1 times 42, I could have subtracted it twice, right? Which is basically what we did here, right? Because you're subtracting, instead of subtracting 42 1, you're subtracting it twice, and when you do that, you get 42 times 51 minus 42, which is 9, which is this number.
Huh.
So that's why the algorithm works. But now there is something extra that the algorithm gives you, and I think that's the next problem. So if you can just pull the next problem.
Oh, yes.
That'd be great. And this is kind of like, do you want to do it in Excalibur or?
Yeah, we
I
can do it
guess.
here.
Okay, does it look good enough?
Yeah, I'll make
Yes.
make it a little bit bigger, and I think that's good.
So now this is kind of like a typical question in number theory. The typical question would be that you want to solve an equation, but you want to solve it on integers or natural numbers. In this case, you want to solve a linear equation. What kind of numbers can you express as 93a plus 42b? Do you have any clue of what kind? And this is kind of similar to that McNugget problem, right? Because in the McNugget problem was, well, how many chickens can I get if I can only buy them in these sizes, right? So this is kind of like the same, but it's like if you could get nuggets, 93 nuggets and 42 nuggets, what type of numbers could you get?
Right.
So far, so good?
Yeah, I remember a part of the idea of this, which is running through this in reverse and doing substitutions.
Yes, exactly. So so the idea here is that, okay, I'm going to start it and then you continue it. Does that
Okay.
work? So
Yeah.
that way. So we start with, because the algorithm is correct. I'm just going to express it in a different way just for convenience, I guess. So you start with 93 and 42. And this is, I'm going to keep track kind of like what I'm doing here. This is going to be X and Y, right? And in the second step to get this 42, I'm scrolling up and down, but I guess you would
Oh
have to
yeah.
scroll up and I guess it's a little too small. You have to make it, yeah. I guess that works. To get this 42, well, the 42, you just move this 42 to the other side, right? So 42 is here, right? So that's just moving Y, right? And to get the 9, you did 93 minus twice 42, right?
Mm-hmm.
So this is the same as doing X minus twice Y, right?
Right.
And the actual operations are, you get 9, right? So okay, so now what happens if you keep doing that for the other steps?
I guess the 9 comes over here.
Mm-hmm.
And then we're doing 42 minus 4 times 9.
Yeah.
And then doing the record keeping x minus 2y, comma, 42 was y. Y minus 4 times x minus 2y. And then actually...
And that you could simplify things there just to get X and Y's. So that way,
Oh, yeah.
like, because in the next step, you still have one step to go. So it might be nice.
Negative 4x plus 7y. And then 42 minus 36 was 6. Okay.
Yeah. And then the last step, I guess. Oh, no, a couple of more steps, so that's fine.
6, and then 9 minus 1 times 6 would be 6 comma 3. And over here, minus 4x plus 7y. And then x minus 2y minus negative 4x plus 7y. Negative 4x plus 7y. Get a 5x minus 9y. And then...
All right. And you don't need to the next step because we already know that the answer is 3 and you already got 3. That
Okay.
3 is equal to 5x minus 9y, right?
Yeah.
Can we verify that that's the case? That 5x minus 9y is 3, just to make sure that all the steps were correct.
Sure. 3 is equal to 5x minus 9y, and then X was 93.
Yeah.
Minus 9 times 42. 15, 46, 18, 37. Oh, that's not true.
that doesn't seem true, right? Where did we mess up something? Let me see. Okay, in the first step we get y x minus 2y, right? That's fine. That's 9. Okay, and then the next step we get x minus 2y, and then you have to take the 42, which was y, minus 4 times whatever is 9, which is x minus 2y. That seems correct. Minus 4x. Is that minus 7 actually instead
Oh,
of plus
how
7?
did that turn into a 7? Should be
Now
a
the 7 is
3,
fine.
right? Oh, no, there's a 4
No,
there. Never mind.
no,
Yeah.
but it's not. Is it plus or yeah? It's plus.
Oh, should it be
Oh, then it's
9? Because maybe I thought
yeah,
that
yeah,
y was
yeah, yeah.
negative. Yeah,
That's 9. Yeah, that's 9. Okay.
that was the issue. Okay.
Hopefully it's not too hard to fix.
So that's a 9. And then that's a 9. That's a 9.
We need
This is
Fembox to help us with these things. I feel that he's the one who keeps us honest.
yeah. 11. Yeah, okay, does 11 fix our problems?
5x. Let's see. 5x.
Oh, what's the
minus
trick
11.
with 11
That's
again?
400. You put the
462?
fourth. Yes,
Oh, hey,
462.
that is
Yay!
3. Okay.
Yay! Yay! So okay, so we can get 3, but if we can get 3, what numbers can we get?
Any multiple of 3?
Any multiple of 3, because we just would multiply by, like, you use that, and if you want 1/6, you multiply by 2. If you want, yeah, you get it, right?
Yeah.
All right. Can we get 0?
By multiplying through by 0, sure.
I guess we can get 0 because we set integers, right? But
Oh, with natural numbers, no.
But yeah, like we could get 0, and we could get also -3, for example, right? By multiplying by -1.
Yeah.
Right. Now, okay, so one question here is this the only solution to this problem? Like, if they ask you to get 3, is this the only solution? Fembox fan, Fembox is sorry. I think you should be, Fembox. Why aren't you on the voice chat? Like, so you know that to get 3, you need 5x minus 11y, right? But is this the only way of getting 3?
I want to say yes. I think so.
And I think this is important, an interesting question, because, for example, when you do linear algebra, you know, like how you have these cases in which, when you have 2 equations, you have either no solution, or 1 solution, or infinite solutions.
Yeah.
So basically, when you have an equation, you kind of always want to know, okay, is this the only way of doing it, or there are other ways of doing it, or not, right? And in this case, so you think that this is the only way, right?
Yeah.
Okay, but what would have happened, for example, if I had done something like 93? I could have done the same procedure, so 93 and 42, but instead of 42, if I have done twice 42 here. But yeah, twice is gonna work because 2 is not a common multiple of this number, right? So if I have done this, I would have got also
we
the
would have just
answer
divided out in
3.
the first step anyway.
I mean, eventually you would have got the same answer 3, because this is the greatest common divisor of these two, right?
But I guess, don't we have different numbers now? Like, to me,
I
this
mean,
is
yeah,
a new
like,
situation.
Yeah, exactly. This is a new problem. Like, instead of 93, I do instead of 42, I do twice 42, right?
Yeah.
So we solved the problem. We would have got also 3, right? But then when you do these other steps, you would have got something here, right? And you would have got some constant x plus some constant y equal to 3, right?
Mm-hmm.
But then these two could be absorbed by the constant of y. And then you would have got a different solution. Does that make sense? Or is it a little
I need to hear
too...
that again.
Okay. Let's actually, is it too much to actually solve this other version of the problem?
I guess not.
Okay, so if you can solve that other version, I was trying to erase. Come on, Scully draw. I don't know why Scully draw don't like when I try to click things. But okay, so let's try to solve that one. So 2 times 42 is 84, right?
Yeah.
So okay, so let's see. And we need to do it also finding the x and the y. So we need to try trace back things as well.
Okay.
Yeah.
9 y x minus y.
Yeah.
9 and then 84 minus 9 times 9. It's minus
9
y.
times.
Y minus 9 x minus y. And Jed, I see your question. We can come back to it in a minute.
Does the answer of 3 has anything to do with the common factors of the original coefficients? Definitely, yet. That's definitely the case. Yeah, like, I mean, the thing is that once you know this, you kind of, once you know more, you obviously think, okay, I can factorize this in prime numbers, and then I can just find the common primes and all that, right? But here we are just using the Euclidean algorithm. Okay, so you got there. So you got that 3 is equal to negative. Can we verify that? That 3 is negative 9 plus 10y.
So minus 9 times 93 plus 10 times 84.
Well, I can do 10 times 84, I think.
Oh, yeah, that's the easy one. Oh wow. Well, look at that.
Okay, look at what you did. Is actually you got something interesting because this y. So recall that when you like this is negative 9 times 93, right? Plus 10 times 84, but 84 is 2 times 42,
Oh,
right?
so we could have done like negative 9x plus 20y in the last problem.
So in the last problem, you could have got also an answer negative 9 and 20, right?
Okay, yeah.
Is that the same answer that you got on the previous one? No, right? In the previous one, you got 5 and 11, but negative 9 and 20 is another answer. So
Okay.
the solution is not unique. So there might be an easier way of figuring out why it's not unique. Fembox says that there is a nice trick. So maybe, yeah. So you see, Fembox, we need you to teach us the tricks, all the dirty tricks in your book. Okay, so we got that, and now the only other question that is remaining is, now you know that you can get any multiple of 3 as an answer, right? Like of the problem 93a plus 42b, the numbers that you can get anything of the form 3 times k, right? For some k. Do you agree?
Yes.
And not only you can get any of these one, you can get them in many ways, actually infinitely many ways. Like, I mean, we just found 2 different ways, but you can get it actually in infinitely many ways.
Yeah.
Do you agree there? Okay. Now, the question is, how do you know that these are all the numbers that you can get? For example, could you get 5 or 2 as well as solutions of this equation?
Mm. Huh.
And yeah, and this one requires a little bit of thinking, I guess. Well, everything requires thinking.
It feels like we should be able to, but I would guess that we probably can't.
Yeah, and let's see why we can't actually. The reason why we can't, let's say that we could get 5, right? Just as an example, but the reasoning is going to be the same. If you could get 5, that means that 93A plus 42B equals 5, right?
Mm-hmm.
But uh, uh, then my claim is that then this would have to be a divisor of both 93 and 42. But 5 is not a divisor. So basically, my claim is that every divisor you should be able to get using this type of equation. Why? Why is that true? Because 93A is equal 5 minus 42B, right? And yeah, why is that true? Okay, now I'm getting confused. So okay, so I'm gonna leave the why for now. I'm just gonna leave it as an exercise for the energetic reader or energetic
Okay.
watcher. Okay, but I hope at least it makes you curious, or like I mean I know the answer is correct, but right now I don't remember the reasoning. You can the only things that you can get are of this form. Okay.
But so if there was some other prime number that divided them both, could we have gotten that one instead of 3?
Yeah, like exactly like the one that you could have got. The ones that you can get are the greatest common divisor, multiples of the greatest common divisor.
But what
Like
about like
if,
the non-greatest common divisor? Like what about some other common divisor?
yeah, that's a good question. What is another common divisor of them? Well,
Uh,
what ends up happening is that the common divisors are precisely multiples of 3, right? 6 is a common divisor, right? Is it? No, 6
no,
is
I don't think
6 is
6 will
it?
go into 93.
No, 6 not. 6 not. 6 is not. But yeah,
We might
like
choose
what would
different
be?
numbers, but
Yeah, maybe this is not like, but what else is a common divisor of these two? Is it only 3? No, there has to be more, right?
um,
Um, 6, 9. 9 is not. 12 is
it's 3
12 a
times
common divisor.
31. They're not going to have anything else.
Oh yeah,
93.
so oh yeah, you're right. But if there were any other common divisor, it would have to be a multiple of this one, right? Because if you think of the picture, what's happening is you have 93 here, 42 here. I'm drawing on that side. 93, and then in the picture, right? Like here you had the greatest common divisor, right? Oh, I see. This is silly. Like any other divisor would be under this one, right? For example, 1 is a common divisor, so no. So the answer is no, actually, right? Because 1, for example, is also obviously a divisor, but any other divisor has to be under 3. In this case, there is only 1,
Okay.
right? Any other common divisor has to be under 3. And then no, like you only can get multiples of this one. Multiples of this one.
Okay.
So that's a pretty good question. It got me confused for a second. All right. So what is the next problem? And again, all this is leading somewhere. By the way, normally you don't do this. Actually, if you want, you can go to Wolfram and just from now on, let's just go to Wolfram and get the GCDs from there. You know, like because yeah, I mean, I think it's nice to or it's good to like do problems like this at least once in your life. And once you feel like you understand them, you can use the calculator. At least that's my philosophy,
Okay.
you know?
Yeah.
Okay, so what do you think about this problem?
Country has a coin system with 2 coins with values x not equal to 1 and y equal 120. Every integer transaction is possible using these 2 types of coins. What is the smallest possible value for x? You want to give 1 to your friend. How can you achieve that transaction?
Yeah, so
So
like
y is fixed at
second
120. X we just know it's not 1.
exactly.
Okay.
So what and there is going to be multiple choices for y, but we are choosing the smallest possible option for y.
Okay. Well, my gut is telling me that I should figure out the prime factors of 120
All
and
right.
choose something that's not that.
Yeah. Yeah, right. Because what you want is what you want. What do you want for the GCD of x and y?
1.
You want that the GCD of x and y to be equal to 1, right? And yeah, since you already know prime factors, the easier way of figuring out a number whose GDC with another number is not equal to 1 is just to check the prime factors, right?
Yeah. And 24 has 3 2s and a 3. Okay.
3 2s and a 3.
Because 8 times 3?
So it's 2 times 3 is, okay, yeah. Yeah.
Okay, so I could choose x equal to 7.
Is that the smallest one that you can choose? I mean, I'm not sure. I'm asking.
Well, it's definitely the next prime number that's not taken. But
Yeah,
if we were to
so,
choose anything with those, I think we get an issue with the GCD.
yeah, because if you take 6, I mean, smaller than 7 would be 6, but then you would have 2 and 3 as a common factors, and if you get 5 is there. So yeah, so I guess it's 7. Okay, so now you know that the other value of the coin has to be 7. Now how can you produce a transaction that makes it equal to 1?
I guess you have to go through the Euclidean algorithm and then do the linear
Or do
combination thing.
exactly. So, but with Wolfram, hopefully Wolfram will give us the answer.
Okay.
I hope.
I guess
It's not too hard, but it's not too hard and is good exercise. But honestly, I think it's actually a better exercise to code it. You know, like I
oh,
mean,
probably.
but no. Well, I guess you can do that, but you can just ask the GDC, and I think it does it because the problem is that now it doesn't know
Oh.
that they are naturals. But just ask for the GDC of A and B, and I think Wolfram does it. Okay,
No.
and if you scroll down, no, doesn't do it. Oh,
Did it say? It says integer solutions.
oh,
Ugh,
oh.
I don't like that.
So I guess the numbers have to be. Well, yeah. How do I interpret that? I don't know.
Yeah, I guess you choose any integer n you want, and you can. Oh, that's kind of annoying.
Oh,
I
so
guess we
that
could choose
gives
n
you.
equals -1.
I mean, just choose n equals 0. Why?
Oh, that's because
And
that's easier.
so
Well, we need a
103 and
negative
negative
coin though
6.
with that.
Well, the idea is that you would have to give some coins, and your friend would have to give you coin backs, right? Coins
Oh,
back,
okay.
like give you some change. But yeah, let's verify that 103 and 6 and negative 6 work.
Okay. So
At
a
the
was
very least.
7.
I guess you can just verify. You can just change a. Well, I guess
3.
on that equation you can change a for
6. Too
times
late.
negative 6.
Okay. I guess that
Yeah,
works.
so that works. Okay, so yeah, I guess that's the idea.
So we're giving 103 of the coins worth 7, and the friend gives back 6 of the
Exactly.
120. Okay.
Exactly. So it's a very easy transaction in that context, I guess. All right, so let's go to the next problem.
Okay.
Did you enjoy that problem?
I mean, I it's okay, I guess. I did not enjoy it.
Okay, that's a start, you know. Okay, let's do the 4 one. What's the greatest common divisor of 2 consecutive terms of the Fibonacci sequence? This one is again not as hard as it sounds, but I just kind of wanna see And Fembox has an answer that seems easier. Well, I guess it's easier if you don't ask Wolfram. Like if you actually have to think, maybe. But since we were asking Wolfram was easier for us. Yeah. So if you don't know how to start, let's just write the Fibonacci sequence and let's try to figure like by observation, and then maybe based on the observation we'll get something. Yeah, I think that's enough, right?
Okay.
So let's start with the first
They
pair.
usually don't have a common divisor.
Yeah, like so 1 and 2, the common that's gonna be 1, right? 2 and 3, the greatest common divisor is also 1. 3 and 5 is also 1. 5 and 8 is also 1. 8 and 13 is also 1. So it seems that it's always 1, right?
Yeah.
But how can we show that that's the case? And for that, maybe 7. Maybe right in here, like I recall that Fn is equal to Fn minus 1 plus Fn minus 2, right?
Right.
So here, like the thing that I was mentioning kicks in because, let's actually move this. Because recall that AB has the same greatest common divisor as A, B minus A, right?
Okay.
So in this case, we want to figure out the common divisor of Fn plus 1, for example, right?
Right.
But then that has to be the same common divisor as Fn plus 1 minus Fn. Is that what I want? Basically, what I want is to add and subtract things around so that I can use the Fibonacci recursion. So what do I want to subtract? Okay, let me think. Fn
Might be Fn minus 1 or
plus 1 minus Fn. So this one would become Fn minus 2, right? Or maybe, let me see. This one is Fn minus 1 plus Fn minus 2. And this one is Fn minus Fn minus 1, right? Can I get something from that? Can I get something from that? Any thoughts, Don, or anyone else? Yeah, like if I subtract this one from this one, I subtract this one from this one.
Plus, or are you already doing the subtraction part?
Oh no, yeah, you're right. This is a plus.
Okay.
Yeah. Thank you. Yeah, like if I subtract those two, can I get something in terms of the previous ones? So because I mean, I guess the idea would be by induction at some point. If you have 1 and 2, we already know that this is 1, right? But this one, since I can do subtraction, I can also do addition actually, right? Because it will be kind of backwards, like going from here to here. Like if I subtract here, it's the same as adding here, right?
Okay.
So this has to be the same as 2 plus 1 plus 2. But this is, yeah, so that's the way of doing it. So if you have Fn plus 1 and Fn, then this is equal to Fn plus 1 plus the 2 of this, which is Fn plus 2. So, but then that tells you that all of them have the same, right? Because you could keep doing this. And then since the first one is 1, all of them have to be 1. Does that make sense?
I wasn't following that, no.
Okay. Okay, so we know that and that's the problem. That's why I prefer it if I don't have to write, because again, when I write, I end up just doing a bunch of things. And yeah, like sometimes my stream of consciousness, I mean, I don't express my stream of consciousness. Okay. So, but yeah, let me see. So we know, this is not the pen. This is the pen. We know that this is true. Like a b is the same as a comma b minus a. All right. So far so good. But then this tells me also that a b is the same as a plus b. The reason is because I could do this substitution, kind of like call this c, right? And then b here would be c plus a. And yeah, and then I changed the name again from C to B.
Yeah.
Right. So do you follow so far? Or like this one is basically the same. I just rechanged the name to C and this one, right?
Yeah.
So if we have Fn and Fn plus 1, this is what we want to find. But this new thing that I found tells me that this is the same as f of n plus 1, comma, f of n plus f of n plus 1. Do you agree?
Yes.
But this is f of n plus 2.
Actually,
right?
wait, should this first one have stayed as fn, or I guess it doesn't matter which one we add it to?
It doesn't matter.
Okay.
I just took this one to keep it because, yeah, again, AB is equal to BA, right?
Okay, yeah.
So yeah, I'm just keeping this one. And then for the other one, I got that database error thing.
I just always click out of that.
Yeah. And then I add them, and then when I add them, I get Fn plus 1 plus Fn plus Fn. Damn it. I wrote it incorrectly. I'm going to rewrite this part because yeah, it's just easier. Fn plus Fn plus 1, right? So far, so good.
Yep.
But this one is F2. Sorry, f of n plus 2.
Right.
Right? And then, but that tells me that any two consecutive Fibonacci numbers have actually the same greatest common divisor, because I can put n whatever n I want, right? So in particular, f1, f2 is equal to fn plus 1 for every n. So far, so good.
Oh, so then we only have to check the first case.
Exactly. Pembroke, okay. I think he has a good idea. For a harder problem, start with Fibonacci sequence with 0, 1, and show the GDC if this is megalomorph. If D equals GDC of AB, then GDC of FA, comma FB is equal FD. That sounds interesting. An interesting problem. And Fembrook has an idea there. If AB and C are consecutive Fibonacci numbers, then subtract. We share it too, and then the common divisor would follow on the left. Sequence, down the sequence 1, contradiction. Yeah, so I guess Fembrook has a different idea to prove it. All right, but I think the reason why I chose that problem was to kind of like emphasize this property of the GDCD.
Okay. Makes sense.
Okay, so let's go with the next one, which I hope is more entertaining. 5.
Okay, got it?
Yep. All right, so well, one of the thing that makes the integers annoying is that there are no multiplicative inverses, right?
Right.
Like when you want to solve an equation, then you cannot just divide. You cannot divide always.
Mm-hmm.
And this is one of the reasons why sometimes we prefer to work modulus a number, right? We
Because you
prefer
do
to
have
work like
inverses.
sometimes you have inverses.
Oh,
Okay, that's kind of like what I want to explore. When do we have inverses? Like for this problem, do we have an inverse? And again, this is something that we could ask Wolfram to do, but I think that at least once it's nice to understand where Wolfram gets the answers from, right?
right.
And then what I like, I'm gonna kind of. Do you have any idea of how to solve it, or how would you solve it first?
Well, okay, so for the multiplicative inverse here would be a number we multiply by 43 that gives us 1 mod 103.
Exactly.
And I've done this before, but it's at least a year ago, and I'm trying to remember how that works.
That's all right. I mean, if you don't remember, it's all right. Like I'm just shoot at any idea that you have, and if you don't have any idea, that's also fine.
I guess we want a number such that 43 times that number A is equal to some other number B 103 plus 1.
Yeah, that's actually a pretty good idea. Actually, so that's a B. Yeah, B times 103. Yeah, that's a pretty good idea. That's what you want.
Yeah, I guess I
And
should be on the right side.
that makes it a little easier to read. Wow, this is actually a pretty good idea because does this look any similar to anything that we've done recently?
Like a GCD.
Yeah, because
And I guess we
you
could always
just
just
want to
make it
find.
plus if we wanted to.
Well,
I don't know if it matters, but
it won't matter because b is an integer, right?
yeah.
So since b is an integer, if you get a number, just take the negative. So yeah, you can put the negative. Yeah, like if you get b, just take negative b instead. So you can change that minus for a plus. And you can, yeah, obviously you would have to also change it in the previous line to make it consistent,
Oh, yeah.
right? Yeah, but it's true, right? Because b is an integer, so you can take just the negative of the number, right?
Mm-hmm.
Okay, so this is exactly the same problem, right? So what algorithm would you use?
Uh,
I mean, we have only
well, you
done
said
one
the word
algorithm.
algorithm, so I assume Euclidean. But
Yeah, yeah,
like, are we
because
doing with variables here?
yeah, because this is so if the GCD of 43 and 103 is 1, you know that the Euclidean algorithm is going to give you the answer to this equation. Because now you have an equation in A and B, where
Oh,
A and B are integers, right? You want
okay.
to basically you want to solve that equation that you found.
So yeah, like we're just gonna find the GCD of 103 and 43, and that'll
But you need
eventually give us
to
the thing we want.
end that way, keeping track, right?
Yeah, okay, yeah. So maybe I'll use the notation that you were using.
Yeah. Or with whatever you feel more comfortable.
Okay. I like the record keeping way that this does rather than going backwards.
Yeah, I also like that. Honestly, again, it's kind of the thing that you do once in your life, like this time, and if you feel that you learn it well enough, that's fine. But for example, the other day, Fenvox was saying that he didn't remember something on the Euclidean algorithm. I'm not sure if this was the thing that you didn't remember, Fenvox. That he was trying to do something and he didn't remember the details. Let's see. While you do that, I'll read the
17?
chat.
Okay, yeah, please do.
Megalomorph says Euclidean algorithm. I don't know if that's a cat pun or
It's not
or
Euclidean, it's Meoclidean.
okay.
Hey,
I get it
Phobos.
now. Euclidean algorithm, you can find the GDC, but you can also show you how to write that GDC as a linear combination of numbers you started with. Yeah, which is what Don is doing right now. Phobos is in the house. Hi, Phobos. Are you surprised to hear me on Don's stream?
Stooky too, hey.
Hey, and Stuki, how's it going? Yeah. Also, on Stuki, are you surprised to hear me on Don's stream? Yeah. I'm not surprised. No, I'm not surprised. I got the announcement. Okay. And then Stuki. Yeah, I'm more surprised of seeing in Stuki. I haven't seen him in a while, actually.
Yeah, the rare Ian Stooky sighting.
Yeah. Uh, Yeah, it's not extremely rare, but yeah, like um, it is a little is rarer than what we wish it was, I guess. Publicity too good. Yeah, yeah. So yeah, I kind of like I'm extorting Don into doing math with me.
Mm-hmm.
If he solves all these problems correctly, his cat mittens will be safe.
Yeah. I'm doing number theory under the duress. That's what it takes.
Yeah, that's the only way of getting him to the number theory.
Oh, this is a nice case. It looks like.
Yeah,
Um.
no mittens. Yeah, and again, the calculations are not that interesting, but again, I think that doing them once is kind of like helps you with the muscle memory. Once if you ever have to do it again, um, you at least know, and you also know what the computer is doing, right? Coding it is also kind of fun because then you realize. I mean, it teaches you things when you actually coded it, like to code the way of keeping track and all that.
Right.
Yeah.
Uh,
And by the way, the Euclidean algorithm is actually pretty efficient. Like, obviously, when you're doing it by hand, it feels like every step is not advancing too much. But you can prove that the number of steps is at most um, logarithm base 2 of the numbers of the
ooh,
largest number that you are doing. So
that's pretty good.
the algorithm is pretty efficient. I don't think there is a better algorithm.
Um. So that was
Euclidean
9
algorithm can
minus.
walk your dog for you, cook and clean for you, improve your sleep. It's the best algorithm. Indeed, I mean, a lot of number theory is just Euclidean algorithm. Like, for example, this thing, like finding the inverse of a number, is just application of the Euclidean algorithm. And that's kind of nice. I mean, I like when you do this type of number theory, you can prove, or basic number theory, you can do the proofs in an abstract setting and not be concerned about the Euclidean algorithm. For example, you can prove the existence of inverses in certain situations. Um, you got the answer?
I gotta verify it, but I
Okay,
think I did.
yeah, it probably did, but let's check it. But yeah, you can prove, for example, the existence of inverses like in a very abstract setting without using the Euclidean algorithm. But I feel that the proofs that actually use the Euclidean algorithm are better in the sense that they also give you like the application. So it's not too abstract, you know?
Yeah.
Megalomorph says, I think it's 2 times bit log base 2. Yeah.
Oof.
Yeah, it's probably, there is probably a factor, but yeah, like I tend to do that thing where I just forget the constants, you know? Okay, so you got the answer. So now that you got the answer, what is the inverse then?
Uh,
Yeah, now
the
we are ready to
inverse
actually
is gonna be a, the number that multiplies 43. The number that multiplies
yes,
43 is 12.
12, right? And then you can also verify it that way. Like you can do 12 times 43 and check mod 103, but we can do that on Wolfram just to
Okay.
kind of like settle it.
12 times 43. Nice.
Mod 100, yeah. Yeah, perfect. No? So this gives you something interesting now that because you have inverses. But now the question is, when you know that you are gonna, like if I tell you find the inverse of A modulo B, when is that possible?
Um. Oh, I guess A and B are relatively prime.
Yeah, You got it, right? They have to be relatively prime because the GCD has to be 1, right? Otherwise, you wouldn't be able to solve that equation, right?
Okay. Yeah. Or maybe
Now,
only
now I
certain
can,
numbers would work.
yeah, exactly. Like an easy case, then, like again, now we are in the problem of A, so inverse or A inverse mod B, right? We are trying to, or we are studying this problem, right?
Mm-hmm.
And then by your observation, we need GDC of A and B equal to 1, right?
Right.
An easy case is if B is prime. If B is prime, because what happens when B is prime for all the numbers between 0 and B?
You're always okay.
Yeah, you're always fine, right? So basically, if B is prime, then you always have inverse. Well, except for 0. Obviously, for 0, you, like as usual, you don't have inverse, right?
Okay, yeah. Mm-hmm.
All right. So now, I mean, this is kind of like taking like, this is not necessarily what I wanted to get into, but let's take a little bit of a sidestep there and introduce something like when you do arithmetic modulo B, you are working in this thing called ZB,
Mm-hmm.
right? This is basically Z, just you are just modding out B. Basically, yeah, the usual thing, right? And then you can have this ZB with addition and multiplication, right? With respect to addition, it always behaves well. You always have inverses, right? But with respect to multiplication, you always have inverses if and only if B is prime. So you already know one side of that if and only if. If it's prime, you always have inverses. Now, for the other side, I mean, I leave it like kind of like as a curiosity for now, right? Now, the other thing is, what if B is not prime? If B is not prime, then another question is, another possible question is, how many inverses does B have? Like, for example, 10. 10 is not prime. How many inverses would 10 have? And again, I'm not necessarily asking you to get the answers. I'm kind of like just putting seeds of curiosity here.
I think as long as the number doesn't involve 2 or 5, you're okay.
Exactly. So in this case, you would have 8, right?
Yeah. Or
Oh, no, no,
no,
because
not
4.
4 or 8.
Okay, so let's
So
actually write
you'd
them
have
down because
6,
now
I
I'm curious.
guess.
So you got 1, 1 is fine, 2 is not fine, 3 is fine, 4 no, 5 no, 6 no again, because yeah,
Right.
because 6 it includes 2, 6, 7, 8 no, and 9 yes. So you only have 4 actually, right?
Right.
And here is something interesting, like 5 times 2 is equal to 10, right? How many inverses does 5 have? Like Z5?
Mm. Wait, 5 mod 5 or wait, I'm
No, sorry,
confused.
sorry. How many inverses mod 5 do you have?
Uh well 5 is if we're working mod 5, everything before 5 is an inverse has an inverse, right? Because it's prime?
Yeah, so how many are there?
Uh 4?
4, yeah, because 1, 2, 3, and 4, right?
Mm-hmm.
And how many inverses does 2 have?
I guess just 1 because we only care
Just
about
1,
1.
right? And then 10 has 4 inverses, right? And 4 happens to be 4 times 1.
Oh.
Coincidence or magic?
Okay, this is ringing a bell because I had a short stint of studying abstract algebra. Is it
Yeah.
actually the LCM that's the general answer for this, or is it
No,
just
no, but
multiplied?
no, you have to multiply them. But
Okay.
like it's. I mean, again, I'm just putting some curiosity there, right? Like in general, the number of inverses mod B is given by something called Euler-Tottien's function.
Yeah, that was like one of the last things that I learned about when I was studying it.
Yeah, so this is phi of, the notation is phi of B, and this is just you can take that as one of the definitions, number of inverses. Mod B, right? Now, by the thing that the observation is that if you have a prime number, then this is P minus 1, right?
Yes.
Right. Now, if you the other thing that you can prove eventually, but probably not today, is that if the function is multiplicative. So this is phi of A times phi of B. So if you want to find the Tottian function of any number, the only thing that you need is find the prime factorization, but then we only know that phi of P is P minus 1. We also need to figure out phi of P to the power of something. And then if you figure out what this one is, and using this multiplication property, then you'll be able to calculate the Tottian function of any number.
Okay.
Okay, and it's not too hard. It's just a matter of counting. Like, for example, for 9, how many inverses does 9 have?
7.
And
6.
Fembox is saying something important. For like A and B needs to be relatively prime in this formula. Thank you, Fembox. And you said that the number of inverses here is 7.
Is 3 and 6 cause problems?
3 and 6, but I mean 3. But you start, so 1. Is it 7?
Oh, so it would be 6 because you would
6,
start
right?
at 8 and take 2 away.
Yeah, exactly. So I don't know how to erase, so I'm just gonna 6, right?
Yeah.
But then, like, I mean, when you think about it, then you realize, I mean, 3 is 3 squared, right? And 6 is 3 squared minus 3, right?
Right.
There are precisely 3 numbers that are not, I mean, 0, because counting the 0, 0, 3, and 6, right? And then in general, this is pk minus pk minus 1. But obviously, you would want to prove it and find a way of proving it.
Okay.
Right. But yeah, I mean, again, just putting curiosity there, because all these things actually, like, I think to understand them well takes time. It's not that trivial. Obviously, it's like everything. Once you know it, it's kind of easy. But before you know it, it's not trivial.
Right.
All right. You want to do the next exercise? How are you feeling?
Sure. Yeah. Let's keep going.
Let's see the next one. I don't remember what the next one is.
Continued
Okay.
fractions.
These ones are, yeah. But let's just do A, for example. I mean, I think that should be enough. We'll get the idea. So what is a continued fraction?
Like a fraction inside a fraction inside a fraction, like.
Yeah, exactly, right. That. And then this is kind of like something that I kind of wanted to connect here. And so the way that you would do it, the way that you find it, right? You want 93 over 42. So this is going to be, how many times 93 fits on 42?
Twice?
Twice, right? So it's twice plus the residue. What is the residue? 84, 9, right? 9 over 42, right?
Oh, yeah, sure.
So this is basically the same that you did for the first step of the Euclidean algorithm, right?
Mm-hmm.
It's basically the same. So, but now I can write this as 2 plus 1 over 42 divided by 9, right?
Okay, and then we repeat the process.
And then you use Euclidean algorithm again, right? So it's 2 plus 1 over how many times? 4. Plus 6
Yeah.
over 9, and then you do it again. So I guess you can finish it right now, right?
Okay. 2 plus 1 over 4 plus 1 over 9 over 6.
Yeah.
2 plus 1 over 4 plus 1 over. So it fits in once, and we're left over with a 3 over 6. So come back over here.
Yeah.
2 plus 1 over 4. What a terrible 4. 1 plus 1 over 6 over 3. And this is going to be 2.
Yeah, so you can just erase that 6 over 3 and just write 2, right?
So this is
All
finite.
right. Yeah, this stops, right?
Okay.
And it basically stops for the same reason that the Euclidean algorithm stops.
Okay.
Right?
Yeah.
And actually, this is exactly the same as the Euclidean algorithm. Historically, so the original Euclidean algorithm probably looks similar to the thing that we did at first. But then I think Gauss realized that you could just write it this way, and then this way of doing the Euclidean algorithm became popular. And then it was someone else later that kind of brought back the original version.
Huh. That's
So,
funny.
but yeah, I kind of wanted to point out that if you start with two numbers that are natural, A over B, both of them are natural numbers, like basically problem version D of the problem, where A and B are natural numbers, then the continued fraction ends. The continued fraction stops. Okay.
Okay.
And now we can do the problem 7 probably.
Sounds good.
Oh, are those the same coefficients that you got in the same problem? Yeah, they have to be, right? That's precisely what we are saying from Fembooks, that but this is basically the Euclidean algorithm. It's just a different way of looking at it, right? But now the question is, what if you try to do the same process, but with something that is not necessarily a rational number? Like square root 2 is not a rational number, right?
Right.
Like, and by the way, like since we are doing number theory, this is saying that the following equation has no solutions. A squared equals 2b squared has no solutions in the integers. Does that make sense?
Uh, I'm. It sort of does. I'm still trying to work through why that's the same thing as saying like root 2 isn't equal to A over B. I guess you could modify it to look like that.
Yeah, exactly. So what you would do is do a squared over b squared equals 2, and this is the same as a over b equals square root 2,
Okay.
right? But this is telling you that that's not possible, right? The thing is that we often don't want to use this symbol because, I mean, if you are working with integers, technically there is not such a thing, right? So yeah, so this I prefer this version of writing it at this level. But yeah, so what would happen if we try to imitate the Euclidean algorithm, but we start with the square root of 2 and 1? So let's see what happens if you try to find the continuous fraction of a square root 2.
So we're starting with root 2 over 1.
Yeah. So that's equal to 1, right? Plus, because the integer part, and in this case is, so
Or rather,
the residue is just the square root 2 minus 1, right? I mean, it's easier to write
okay,
it
yeah.
that way. I know that is kind of silly, but maybe put in a parenthesis between, yeah. And then you do the flipping as before. But you can rationalize that, the thing on the denominator, right?
Okay, yeah.
Over 3, right? And now you can,
Oh wait, did I do that right? That might be 1. No,
yeah, I think is it 1?
because
Yeah,
root
it's 1,
2
right?
plus 1. Yeah, okay.
Okay, so now you can take the denominator and do it again, right? Because how many times does that is a square root of 2 plus 1 into 1?
Uh, I guess
Well,
twice.
yeah, twice, right?
And then whatever is left over. So like root 2 plus 1 minus 1?
Minus 2, right?
Yeah.
Minus 2. And then what do you get?
Uh, root 2 minus 1 again.
Yeah.
So
So what?
we would basically repeat this process.
Exactly.
So if I were to skip a step or two, I
Yeah.
think we get,
Or 3 or 4. You can skip it.
yeah.
Not till that you can skip as many steps as you want, right? Because you probably notice what's going to happen.
Yeah, I think we're going to get
Now,
kind of twos down that line.
so now it's not going to be finite, right? Like it's actually the continuous fraction is going to be forever. But in this case, it has the property that it actually repeats. It's always 2,
Mm-hmm.
right?
It's kind of funny that it repeats in this form. When,
Yeah,
yeah.
it's interesting that it repeats in this form, but it's kind of similar. Well, continued fractions are just another way of representing real numbers. We usually represent a real number like square root 2, we would usually do 1.4241, whatever, right?
Mm-hmm.
But like this is just a different way. In this case, often something like this, people write as 1, then a semicolon, and then just the rest, right?
Oh, yeah, yeah.
And when you represent numbers on this way, sometimes the number repeat. For example, 1 over 3 is 0.3333, right?
Mm-hmm.
So we know that numbers repeat when you represent them this way. Number repeats when a and are of the form a and b are integers. Now, an interesting question again, not something that I'm going to answer, but is when does the continuous fraction repeat?
Um,
If it's there's some reason when they repeat or not. But I can say like if the number comes as the solution of a quadratic equation, it's gonna repeat. That's something that
oh,
is
that's
not hard to
like
prove.
transcendental is the word?
Well, no, like that's algebraic. Like, but
Okay.
it's not all algebraic. Like a number that can be represented as the solution of a polynomial is called an algebraic number, and the numbers that are not algebraic are transcendental,
Yeah, sorry, I meant
as you
like
said.
not transcendental.
Exactly, not transcendental, exactly. But not all algebraic, some algebraic numbers don't repeat actually. Only the ones that are solutions of polynomials of degree 2. Basically, if you get it as the solution of the quadratic equation, then they repeat.
Huh. That's weird.
Yeah. Yeah, it's interesting. But now, I mean, because I kind of want to give you something useful.
Okay.
So what happens if let's actually do this calculation, but let's truncate it. So we will start with 1. So let's say that xn is equal to this, but you only go up to n level. For example, x1 would be 1. No, or let's do x0 equal 1 actually. X0 equal 1. X1 is equal 1 plus 1 over 2. So what is this one? X2 is equal 1 plus 1 over 2 plus 1 over 2. I don't know what this one is. Okay, so let's calculate those numbers that I didn't. Like, I guess the first one is 3 halves.
Right.
3 halves. The next one would be, what would be?
Um,
5 on the denominator. 2 fives. I don't know.
7 over 5.
7 over 5. And maybe let's do the next one. Mm. Mm. But that other part, okay, I guess you can repeat the calculations, right? Not a big deal.
Yeah, I guess that part we already said is 2/5.
Yeah.
is equal to 17 over 12.
Yeah, and these are how how well these things approximate the square root of 2. I guess the question is how fast this thing actually gets to the limit, which is the square root of 2. And it turns out like this is related to the following question. Like we know, where is 7? Okay. We know that again, and what I said earlier, a squared equals 2b squared is never, like this has no solutions, right?
Mm-hmm.
But maybe we want to find a over b kind of close to square root 2 in some sense.
Okay,
right?
Yeah.
That kind of makes sense. Sometimes maybe you just want a good approximation of a square root of 2, right?
Mm-hmm.
Now, maybe this one has no solutions, but maybe the equation a squared equals 2b squared plus 1. Like, since I know that this has no solution, maybe if I put a plus 1 here, maybe I'll get some solutions. Square equal 1, right? And or plus or minus, because basically I'm allowing for some error. And the smallest error that I can make is 1, right? Because I know that I cannot make error 0. Like if I consider this as the error, I cannot make error 0 because that would imply that the square root of 2 is rational, which is not, right?
Yeah.
But let's see what happens with the fractions that we got. We got the first fraction that we got was, well, 1, 0. The first fraction that we got was 3 over 2. And if you put a equal 3 and b equal 2 in this equation, you get a squared equals 9 minus 2 times 4. So you get actually 1. And what happened for the next one? The next one that we got was 7 over 5. So 7 squared minus 2, 5 squared. So this is -1, actually. Are you following?
So wait, do you just guess the A and B that would give us this?
No, I didn't. What I did was look at the numbers that our continuous fraction gave us. So we got 3
and
over
2.
2,
Okay, yeah.
3 and 2, and I use a equal 3, b equal 2. Right.
Okay.
The next number that our continuous fraction gave us was 7 over 5, and I'm seeing what happens in this equation with 7 over 5. Now, can you verify the next one? 17 over 12.
17 over 12.
Yeah, just to make sure that the idea is getting.
I can verify that in Wolfram Alpha because I don't want to square 17.
Yeah. That's fine. That's fine. As far as you get the idea. I once calculated 100 billion digits of a square root of 2. Wow, that's crazy.
That is 1. Huh.
Yeah, and then if you keep going, it turns out that each partial solution to the continued fractions satisfy that equation.
Weird.
Right? And interesting, this is kind of interesting because, again, this is basically what number theory studies. This is a Diophantine equation. I don't know how to spell it in English. Diophantine equation, which are equations in which you want the solution in the natural numbers or in the integers. This is just a type of Diophantine equation. If you wanted the kind of, in some sense, the best approximation to a square root of 2, then you can do this, find solutions of this equation, and then you know that your number a over b is gonna kind of approximate it well, because your error is just gonna be kind of this little one that you have there. Does that make sense?
Yeah, I learned about Diophantine equations ages ago, but not with this perspective about them. With like continued fractions.
For example, who was False was saying that they did. False said that they'll calculate a lot. I don't know. Someone was saying that they calculate a lot of solutions.
100 billion digits
Uh,
square root 2, I assume with programming, not by hand.
yeah, yeah.
But
So
maybe.
one way probably of getting more and more. I don't know if this would work, but maybe it would be continue the procedure and try to get more integers, right? And then just do the division. I don't know. Maybe well,
Yeah,
maybe
I
this is
think the
not the
continued
best way.
fraction isn't that bad to program.
Yeah, yeah, it's probably not that bad, but yeah. So obviously the problem with calculating many digits is because the limits of the computer, right? It becomes
Hmm.
very hard because we only have, I don't know, the 64 bits. So yeah, so you start losing precision after not that many digits actually.
Yeah.
But yeah, and Fembooks, for example, just by playing around, is sharing like a formula, right? So if you have A over B, if you already have one, the next one you can get it using that recursion that Fembooks found there.
Oh, so if we already
Uh,
have, say, 3 over 2, we could immediately get to 7 over 5 with what Fembox did.
exactly. I mean, obviously, the way that he found that formula probably was just by playing symbolically with what we were actually doing and figuring out that the next step is going to update it in this way, right? Because since it's kind of recursive, right? So it's probably not hard to figure out that there is a recursion for that,
Yeah.
right? So yeah, like as Poingalis is saying, this is an example. This type of Diophantine equation is called a Pell equation, and it has a lot of interesting relations with. It's a good example for learning some problems in number theory and also in algebra, in abstract algebra, because it tells you yeah, it tells you like when can you factorize. The next idea here would be to extend the concept of factorization to other numbers, other types of numbers, and the Pell equation gives you like good examples for doing that. Yeah. Yeah, so what do you think so far, Don? How do you feel about it? I mean, I appreciate that you gave me the chance of make you do number theory in the name of mittens, I guess.
I mean, so I'm still not a fan of the restrictiveness, but this is a lot cooler of a perspective on it than I had before.
Yeah, like I think those problems are fine. I think the last problems, let's just quickly show them, but let's not solve them. I know that you are probably already tired of this and people probably want to see other type of problems.
I mean,
Um,
I don't
the,
mind,
the,
but
the other problems are actually harder. So I kind of just wanted to get there and just leave you with some problems that you may want to attack at some point and make you curious about, because obviously number theory is gigantic, and I think as far as you are able to kind of like make someone curious about something, maybe they'll get some love for it eventually.
yeah, maybe I can like give these a try on like Saturday after the reading group or something.
Yeah, that could be fun. I mean, I'll probably join and try to help. Again, these ones are a little harder. The last three are a little harder, so they would
Okay.
require more. So I think it's a good point to just let it sit and what I like to do when I finish something like that is to try to, well, okay, what did you learn? Just kind of like do like a summary.
What did I learn? I definitely learned a more like convenient way of doing the Euclidean algorithm with that notation. I think I preferred that to the way I was taught.
Hmm.
Um, and then also the connection with multiplicative inverses in the Euler-Totient function. Maybe I knew that, but I've definitely forgotten about it.
I think those are pretty good takeaways, really. Those things are actually pretty good.
Yeah, and also the continued fraction thing. So I was very confused with how it would work for an irrational number, but
Yeah, like obviously, like all these things are easier to do with a computer, but you can, for example, try to find the continued fraction for e or for pi. It's much harder though. It's much harder, but yeah, I mean, it's much harder the operations, right? Like in this case, since you get that recursion, you
oh
kind
yeah,
of
you can't
quickly realize.
rationalize.
Yeah, but like as you said, like pi and e are transcendental, so their their continued fractions doesn't repeat. So you would actually need to keep doing calculations if you want to keep finding numbers in the continued fraction.
Right.
Yeah, so that's it. The other thing, I mean, I think those are great takeaways. The other thing that probably would you might find useful is what I was saying of picturing the numbers by divisors, like kind of like growing as divisors. So you know, like the meaning of the GCD is that is the one that points down, and the LMC is the one that points up.
Right.
The thing at the very beginning. I think that's also kind of
Yeah.
like an important insight. And by the way, like when you think of that, of numbers in that way, of natural numbers in that way with divisors, I don't know if I erased it, I think.
I think we did. Yeah.
Yeah, because it was missing the yeah, the Scully draw. But when you think of numbers on that way, they happen to form also like an order, just like you have transitivity and all the properties of an order. It just happens to be a partial order instead of a total order. So you don't have trichotomy. But yeah, so that's also like a good insight. But yeah, I mean, this is it. This is it. This is what I have. I hope you
So,
enjoyed it. And go ahead.
just thank you so much for your time and for putting this together. It was neat.
Yeah, and also like Fembox and I are gonna start reading a book in number theory after you finish the relativity one. Actually, if you want to actually organize that reading group, if you feel like you actually want to do number theory, we could do it on your stream. I have no problem with that. But I don't know if you're that interested in number theory. If you fell in love that hard, or are
I
you?
probably would want to organize it. I'm more just concerned about like I want to make sure I have a lot of free time going into grad school.
Yeah, yeah, that's true. That's true.
Um,
So
but
you are
maybe
not
for at least for the early ones, maybe I can like hop into to or something though. Depends how
oh,
much
definitely, definitely,
the reading is, but at least advertise it
definitely.
for you too on my Discord and
That'd be
stuff.
awesome. But yeah, I mean, if you want that, so it seems like you are not simping that badly for number theory, but you fell a little
No.
bit in love. You're just,
It's also just I only
you're,
have so much like brain power, and I want to study certain things before I start
definitely,
up. So
definitely, that makes total sense. Yeah, I hope you enjoyed it. And so, Don, would you be, after you seen a tutoring session with me, would you be willing to pay $1 million for another one?
not $1 million, but that's certainly
Well,
like this is a very like valuable thing that you gave me. So thank you.
the good news is that you don't need to pay $1 million. You know, you can just ask. So yeah, like if you ever want, we can do it again. And yeah, thank you. I mean, it's fun to try to think of ways of making this a little bit more interesting. I think that something that you would enjoy would be to do at least the RSA. How does the cryptography thing work?
Oh
I think
yeah,
you would find it interesting.
that could be a cool
Uh,
one.
yeah, maybe one day we'll do it and we'll see. But yeah, thank you so much, Don. And yeah, I guess I'll leave you to the rest of your stream. I'm not sure how much are you gonna do, and I hope everyone enjoyed it. If anyone find it interesting, feel free to join my Discord server, and I'll we can talk a little bit more about it. And again, if anyone wants to do the join the reading group with Fembox, we are doing it on Saturdays at 2 p.m. Eastern Standard Time. So yeah, everyone is welcome.
Awesome. Thank you so much.
No problem. Any other final reflections or anything else you'd like to mention?
I don't think so.
All right. Okay, thank you. Then I'll just disconnect from the call and just join the stream as normal.
Sounds
Does
good.
that work?
Yeah.
Okay. Thank you, Don, for having me, and I'll see you on the other side. Bye-bye.
Talk to you later.
Yeah, bye.
Awesome. That was great. So yeah, guys. If you're not already doing it, follow Slim. He's an awesome dude. As well as his YouTube channel. I really should have had the link ready. That would have been the nice thing to have ready, but I didn't think about that. Let me grab it quick. Also, hey Sage. I was gonna type hi to you, but I know that you would want to hear it. Mittens is safe, yeah. There you go. Also, check out his YouTube channel too. Okay. Let me get the music going, and I'll switch my stream title, and we'll just do kind of regular math stuff. Oop. Okay, good. You can take down that pin as well. I feel like I'm oh yeah, title. Duh. Answering math questions from chat and studying. And let me update the YouTube information too. Where's my text file? Here it is. Femvox, I have not even started the relativity. So I don't know. It's not looking good. We're in the same boat. It might just get delayed a week. Okay. Ooh, famous. Yeah, we can draw that. By the way, guys, I tried to switch the Excalidraw to dark mode, but for reason Excalidraw just hates. I think Excalidraw hates me as a person. And when I put Excalidraw into dark mode, it started lagging terribly. But for the stream, I'm going to start trying to use dark mode. I don't know if people have an opinion on that, but either way, if someone does have a strong opinion, let me know. I probably just won't be able to... I'll have to troubleshoot why dark mode of all things would lag Excalidraw, but at least for Journal++, it's not a problem. Okay. Light mode for life. Honestly, that's how I feel. But I feel like people who like dark mode really like dark mode. Or like they just like can't use like light mode. Whereas for me, certain types of dark modes at least kind of hurts my eyes. So I tend not to use it. I think this will be fine with my eyes though. Using dark mode on OneNote. Okay, let's do famous draw it. I'm glad I can finally actually do one of your drawings, famous, because I feel bad that I've said no to so many of them because it's just wasn't a good time. He microwaves fish in the office. Come on, there's nothing wrong with microwaving a little fish in the office sometimes. I did I say hi, famished? Either way, hi. From one F star M to another. Yeah, if you take Femvox fan and divide out famished edits. Okay, you know what? This is too many letters to write. But I want to make a joke about canceling the F's and the M's. I don't want to write out everything else though. Hey, Milk. Now prove the square root of all numbers that aren't perfect squares are irrational. I was just like I've learned that proof at least twice, I think, and I know you start with the contradiction that root 2 does equal a over b. I don't remember at all how you proceed though. Hey, Lucas. A whiteboard with math and a person trying to think of problems. Okay, we can do that. Do we have a rounded rectangle tool? We sure don't. That's as good of a whiteboard as I'm going to get. R is both open and closed. Ooh, I think I've actually done that. Well, no, I don't know if I've shown that. I've said that. I'm going to do this drawing, Lucas, and then yes. Hey, Samrud. A whiteboard with math on it and a person trying to think of problems. Okay, so let's draw the person first, and then we'll put the math on the whiteboard. He's gonna look like he's trying to use his mind powers on it. Okay. Like, is it just a common human experience that we've all tried to use mind powers on things when no one is looking? Like, just to see if you have superpowers? Infinity. Yeah. We can definitely do that. Oh, and Lucas, that reminds me, I need to correct myself about my correction, because the last time we talked about infinite integrals, I said something that I thought was wrong, then I corrected myself, and then I think I've now realized that I was right initially. Too scared to try for superpowers, you're pretty sure you succeed. And I feel like whenever I have to write generic math, the first thing that always comes to mind is the Gaussian integral. I remember what we were talking about, and so I'll say that in a second. Two sets A and B containing 4 and 5 elements. Find the minimum value of A union B. A union B. Let me just do that quick, because that's a fast question. Can't study or focus. I need to study 5 to 6 hours minimum. Probably don't be so hard on yourself. If you literally can't study, then don't try to study. Just get rest. That'll serve you so much better than trying to force yourself to study. I wouldn't set arbitrary hourly goals for studying, because that's how you burn out and do worse. The quick answer to this, Samroot, is that at a minimum, A union B includes all of A. Well, not at a minimum. It includes all of A and all of B. Oh, cool. I was gonna add a little bit more famished. I'm glad that you're happy with it so far, at least. And so in the worst case scenario, let's say, like, let me just give it the worst case. If A is 1, 2, 3, 4, the smallest we can possibly make the intersection is if B has the same elements. 1, 2, 3, 4, but B has length 5, so we have to add on a 5th one. So if we union these two things, we're just going to get B. So the smallest A union B can be is 5. Because we can always make it bigger. Say if I erase the 1 and make it a 6, then it's going to be like 1, 2, 3, 4, 5, 6. But we can't ever go smaller. So that's how you do that, Samrud. What's other generic math? Limit definition of a derivative. And then square root 2 equals A over B. There we go. Thank you for the redeem, famished. So if he has a strong jawline, he does. I was about to say cleft chin. It's not really cleft chin, but Territar. Any advice for how to tutor others? That's a great question. And like people in chat, feel free to pipe up. Whenever I tutor someone personally, the first thing I try to figure out is what their background is. So like even when people pop in chat, it's so much easier for me to explain something to someone who I know what their level is and the things that they are strong and weak in. And I kind of tailor my explanation to that. So if they're weak in something that I think is important, I'm going to try to explain things using that thing to try and help them get stronger. It means please. Oh, funny. And so that's probably like the biggest thing that it's going through my mind whenever I'm tutoring someone. And that, like, I try to just like build rapport with students, like make it at least somewhat fun to hang out with you. And to the greatest, actually, this one kind of varies by the student, but to the greatest extent possible, if you can make them do the work, that's usually should be the goal, to let them do as many things as they can on their own. Figure out level there, then figure out what's the best way to explain it to that certain person. Some might prefer purely theoretical, some might prefer... Yeah, and so like Lucas, with you, like you're one of the people who I probably know the best to like ask questions here, and so I definitely explain things a certain way whenever you ask a question. Empathy is key to great teaching. They might learn in different ways than you do, so you have to figure out the way that they learn. Yeah. So yeah, Tartar, are you about to like start up a tutoring job? All right, so Lucas, the thing that we were... this is actually... So you're asking about integrals out to infinity? No, it is a good thing. Sorry, I mean it in like a... well, yeah. I mean, like, I have a lot easier of a time explaining things to you because we've gone back and forth so much that I feel like I know you, like, pretty well. You're gonna tutor a cousin? Oh, nice. Okay. So the thing that we were talking about last time is if you just take the equation y equals x, or you know, f of x equals x, we're talking about the average value of this function out to infinity. And so what I did is I set up the integral, the limit as b goes to infinity of 1 over b minus b from minus b to positive b of x dx. And so there's a lot of b's in this, but this is just a version of the general formula for the average value, which is 1 over b minus a from a to b of f of x. And so since we want to go out to plus and minus infinity, I just made these the same letter, one positive and one negative. And so we did this and I got 0. And I was surprised by that. Let's try and get it again quickly here. Yeah. So this is a really weird thing that I still don't like fully understand myself. I mean, it's subtle at least. Wait, I'm not getting the right answer here. What did I do wrong? Oh wait, no, I'm sorry. That's 0, right? Is 0. Okay, and so that 0 is what I was surprised by. The thing is, we could also have thought about this integral instead as like I'm gonna make like kind of a breakpoint at 0 and do two different integrals, one out to positive infinity, one out to negative infinity. And so we can even just forget about the average value bit. So I do the limit as a goes to negative infinity, integral from a to 0 of x dx, plus the limit as b goes to infinity of 0 to b x dx. If we do this instead, because like, so in theory, this is the same exact thing. If you like are thinking about like the picture of what's happening here, all we've done is kind of split up into two pieces. But if we actually like go through and do it, we're gonna get something that's different. Oh wait, okay, well, yeah, I split it. I guess yeah, we can still include the average value bit. 1 over 0 minus a, 1 over b minus 0. And so honestly, like the average value part isn't like the most important part, but we can keep it. X squared over 2 from a to 0. One over b, x squared over 2 from 0 to b. So following this integral through, from 0 we get 0, then from a we get minus a squared over 2. We're nearly there. I like the actual algebra of what I'm doing here is the most important thing. The important thing is that the result we're going to get at the end here. So the negatives cancel, and we get just a over 2 plus limit as b goes to infinity, b over 2. So from this piece here, this is the important part, we get negative infinity. From this piece here, we get positive infinity. So this is basically infinity minus infinity, and we would call this an indeterminate form. It's not necessarily 0. We just don't know what to do with this, usually. Yes, and so like that, it's just a weird thing where if you split it up into two pieces, you just can't really say what the result is. If you do it in one piece, you do get 0. And so for reasons I'm not completely clear on, I mean, I'm sort of, for reasons I'm only like sort of clear on, it turns out this second way is actually more general and the thing that you would consider kind of more interesting. Because not necessarily. Like a and b can go out at different rates to infinity. The difference is in the first situation, we are going out to plus and minus infinity at the exact same rate. But here, a and b don't necessarily follow the same path. Like they don't have to be the same thing. Whereas in the first case, they do. And so that's like a... Can you use the first case to solve the second case? Uh, no, because we've just shown they're not necessarily the same thing. Like, you can go the other way, where the second case, if the second case works, then the first thing up here definitely also works. But the reverse isn't always true. And so what I've just been learning from the complex analysis book that I've been reading actually is that you like what's commonly done is you use some type of test to see if this thing converges. And if you prove that it converges, then you can usually go ahead with this simpler version here. But this is like, it's like a one-directional thing. Like, if this works, then this up here definitely works, but not always the other way around. So it's a really weird, unintuitive thing. Well, an indefinite integral is something else. An indefinite integral means you have no bounds at all. This we'd say is x squared over 2 plus some constant. If you mean infinite, then yeah. But I'm being picky about wording. Like, this one is infinite. Okay, yeah, it was just a wording thing. Okay, I'll make sure that we were clear on that, because indefinite is a different thing. Okay, okay. But yeah, so did you want to talk about infinite integrals in general, or do you have like a separate thing that you wanted to ask about them? That's what I like wanted to mention about them, but you had a different question, I think. Oh, FA. Thanks for the follow. I I I I assume you're the one who I played Repo with the other day. Aren't they always minus infinity plus infinity or 0? Can you actually do math? I sure do. I try to. Aren't they always minus infinity plus infinity or 0? That's a good question. I'm thinking about it. It's you? Oh, nice. Yeah, thank you. And yeah, I completely understand if you don't want to hang out for a math stream. I do also play games on stream, but yeah. I appreciate you. I try to think of an integral that would converge to something else. Because I feel like that's possible. I'm just trying to engineer one. What does, okay, just as an example, I don't know if this is going to work or not. From 1 to infinity of 1 over x squared. Oh, and I should say, infinity up here isn't technically valid. I usually do it anyway because it's easier to write. But the better way of saying this is b goes to infinity, or whatever letter you want from 1 to b. That's just a pain to write every step, so I don't usually do it. But this is the technically correct version. But I think this infinite integral will converge to something that's not 0. So 1 over x squared will integrate to minus 1 over x. that when we're writing that from 1 to infinity. So minus 1 over infinity, which is terrible to write, but I'm doing it, plus 1 over 1. That's 0, and that's 1. So I guess the answer to your question is no. They can be any number you want. Well, the interpretation of it is still the same. So 1 over x squared looks like this. And so I did the integral from 1 to infinity. So I'm getting this area under the curve here. And this area definitely doesn't look like 0. Now I chose 1 over x squared specifically because it drops off fast enough that it still converges. Like this part over here gets small fast enough. If you tried this with 1 over x, it actually would not work. That's like the break point of when it doesn't work. Beginner at stuff. Oh yeah, that's another example too. So actually, we can talk about that one too. Actually, I should have started with, do you know that integration gets you the area under the curve? Because I forgot you haven't like you're studying ahead. Okay, good. So yeah, it does go off to infinity, but the weird thing is that doesn't mean this area is infinitely big. It's just a very weird thing that comes up in calculus where this thing that's infinitely long is just one number. And you learn about that in other contexts too. So now we're getting into series, which is the other context I was thinking of. So the example you give, 1 plus 1/2 plus 1/3, this does shoot off to infinity. You're absolutely correct about that. This infinite sum you can make as large as you want. And so I would think of this one as 1 over n, the sum of it. But if I magically make this 1 over n, or I throw that out and I make it 1 over n squared, so it's 1 plus 1/4 plus 1/9 plus, this is actually going to go to a certain number. I think it's pi squared over 6. It's a little bit hard to actually prove that. Okay, yeah, I called it right. Thank you, Slim. And so it's just a weird thing. Yeah, exactly. It's so weird, right? It does not shoot off to infinity. And the huge difference here is the power. 1 over n drops off faster, or sorry, 1 over n squared drops off faster than 1 over n. Like 1 is the magical breakpoint as it turns out. Maybe understanding series first would help, like seeing the geometric series sum with infinitely many elements. Yeah, and so that a simpler thing to kind of see why this works is, let's just think about a square. Oh, I hope I can do this right on the first try. I might not do it right on the first try, but we can take a square. If the side lengths are 1, then the area of the square is 1. Mostly that they exist. Okay, that's something. But I could also cut this square in half. And I'll get that this area is 1/2, and this area over here is also 1/2. But, oops, I could cut this half in half again. And I'll get 2/4, or, you know, 1/4 and 1/4. And then I can cut this one of these quarters in half again, and I'll get 1/8. And I can do this infinitely many times. I'll stop at this last step here. And so if I did this out to infinity, it would look like a half plus a fourth plus an eighth plus a 16th plus dot dot dot, like, you know, 32, 64, 128. I can write this with summation notation from n equals 1 to infinity. These are powers of 2 down here. So 1 over 2 to the n. And it's more common to write it in parentheses like this. They're both right, though. Oops, sorry, n. So this is probably a better first example to see of a series that goes off to infinity, but because of this geometric kind of interpretation, we know it equals 1. It's infinite, but it still just is 1. No, it's 2 to the power of n, because we go from 2 to 4 to 8 to 16. If it was 2 times n, it would be 2, 4, 6. Because we're dividing by 2 each time, not subtracting 2. Or something like that. Oh, I'm glad to hear that. Big internet stuff. And so, yeah, when you first get introduced to series, it's probably one of the first things you see as an example of something that's infinite, but still converges. It's a really crazy thing, but it works. And so, and this it's like a building block. Like you use this is called a geometric series because it has this geometric interpretation. And it turns out, as long as this thing inside the parentheses is less than 1, the absolute value, if we call that thing r, this thing will converge whenever the absolute value of r is less than 1, or equivalently -1 less than r less than 1. So if you did 2 to the n, then yeah, that's going to shoot off to infinity. Clarify as needed. What part? I guess I'm trying to say, like, we have 1/2 to the n here, but it could have been any other number that's less than 1. So, like, I guess I'm trying to answer the more general version of the question of, we just showed 1/2 to the n converges, but what other things inside the parentheses would also converge versus shoot off to infinity? And so the answer I was trying to say is that as long as that number is less than 1, you're okay. Oh, really, Zach? Oh man, I shouldn't. Okay, I shouldn't have just assumed that. Thank you for the correction. Why would it not? Okay. There's probably a historical reason for that, but like I thought that was just kind of a given. Yeah, so Lucas, I guess we call that number r because we think of it as the rate, and Yeah, it's because mathematicians like to think about, they like to like generalize things. That's why we go that direction. I am so I guess I can kind of see that with geometric and arithmetic means. But like that's such a cool geometric interpretation. Like why would it not be called geometric for that reason? Huh. Okay. And see, I remember when Zach or E2 was teaching his infinite series class, he found another way of explaining a geometric series using like you're eating part of a sandwich and like you eat half, you pass half to the other person. They eat half of that, and then and that sounds kind of gross now that I said it out loud again. Like just cut it in half, but you know. How do you define x to the I? Because like what? Yeah. If you have x to the I and you need to deal with that, you can do what Zach said and do e to the power of I ln x, right? And so you could do something with that. Yeah, and so this will just be a complex number now. I'm assuming that x is a real number here. And so, yeah, this will just be... It's a complex number with magnitude 1, or modulus 1. And ln x will be the angle. I guess this would only be valid for positive x, but if it's negative x, you can probably do some manipulations. But yeah, usually when you have like weird powers like I, you kind of look for some type of trick like that. If you asked me instead about like z to the I, and z is a complex number, I would have said take z equal to re to the I theta, just the general like polar form of a number. And then you have re to the I theta to the power of I, and the i's would multiply. Which I guess is now a real number, isn't it? That's kind of weird. Oh, sorry, it's r to the I. And then that's a real number to the power of I, so you do that thing, I guess. That's kind of funny. Raising something to the power of I like switches the argument and modulus. That's kind of funny. This is now the modulus, and that's the angle. Yeah, look, if you have any other questions, feel free to ask. If not, I'll look for something to work on my own. No, it's not really my usual like listening rotation. I could put it on if you want. Any proof for why an integral is the area under a curve? Ooh. I think it's another thing where that's a definition. We define the integral as the area under a curve, and we later prove that the integral is also the antiderivative, like the opposite of taking the derivative. You have the CD in your car? Oh, nice. Uh, WBBSC class. That looks like a terrible problem. I hope you're not forced to do that by hand, because I don't know how you would really do that without taking an hour to move things around. Shuri, 3 plus M sign. Huh. That's an interesting problem. Why is an integral the antiderivative? Well, you basically need to take a whole semester of real analysis to really learn that. uh, the short answer is that that's the fundamental theorem of calculus. The actual proof of that is not long, but it requires another theorem. And if you ask me to prove that theorem, it's going to require another theorem. And that progression of theorems is basically like your first semester of real analysis. Yeah. Use the mean value thing for integrals. I remember that from your class, Zach. So I wouldn't be able to explain that one simply, unfortunately. This is the one we want? Yeah. Hey, collar cone. Oh, yeah. Yeah, I bet I remember exactly how this proof works, but I don't know if that's what you like would want to see. Um, am I winning? I think so. I feel like I'm winning. Just earlier where Slim was showing me like the basics of like number theory and trying to like get me interested in it. So that was like a fun little like collaboration. And we've been talking to Lucas about like infinite series. You'll take a look at it. All right, sounds good. Because I want to work on Shuri's question too. For now, good night. Sounds good. Thank you for the questions, Lucas. Hope you sleep well. So I think we can just take a derivative here. I hope it'll be this simple. Wait, M controls the amplitude, right? Why would M affect anything here? Just goes your class for the fall in the class you like to TA. Ooh, that's exciting. What classes? So that we said that equal to 0 for a max for a critical point, and then for a maximum we want that thing to be negative. What's the smallest possible integer that has a remainder of 1 when it's divided by any of the numbers 2, 3, 4, 5, or 6? It's breaking my brain. I'm gonna finish off this question and then think about that more. And so I think there's infinite I think there's as long as m is positive, I think you're okay, because all m does in this function is it controls the height of this sine wave. I'm pretty sure. Let's go to Desmos and verify this. Maybe it's none. Wait, is it inclusive? No, it's inclusive. And then x equals pi over 2. So long as this maximum is between 0 and pi over 2, we're okay. And yeah, look at that. As long as m is positive, I mean, I guess 0 is also fine, technically. But yeah, sure, any m greater than 0 is okay, or equal to 0, I would say. Two special topic classes in algebraic geometry and one class on PDEs. Ooh, nice. For grad school, they have these like journal clubs that meet like once a week. It's just like a one credit class. And they said it's a good thing to do if you want to like stick out when you're applying for a PhD. And so I'm trying to decide which one I want to do. There's a mathematical biology one, there's a PDE one, there's an applied analysis one. I don't know, there's a bunch that sound like interesting. Wouldn't it have a remainder 0, Fizzbuzz? Or wait. Am I dumb? Smallest positive integer has a remainder of 1 when divided by 2, 3. No, wait, 1 wouldn't work, right? Isn't that the wrong way? Because 1 divided by 2 has a remainder 1. 1 divided by 3 has a remainder. Oh, wait, never mind. That is fine. Apparently, I've done too much number theory today because I can't. Because I'm like struggling with that. Let me read Puika's comment too. Okay, wait. I'm doing too many things at once. Let's copy in Fembox's question. And then read Puika's comment. Linear curve under f of x is some starting point up to x. If you move a tiny bit from x to x plus dx, the extra area gains approximately a small rectangle height f of x with dx. Change small area is about f of x times dx. It means the rate at which area grows, the derivative of the area is just f of x. Ooh. Oh man, that might be a good explanation to give to Lucas there. You're into the curve, some starting point up to x. If you move a tiny bit from x to x plus dx, the extra area gains approximately a small rectangle height f of x with dx. Shuri, for the question as you typed it in chat, there's no way that's it. The only thing m does is control the height of the sine wave. So unless there's a typo in what you wrote, there's no way it's that. When I was doing masters, we organized a few student seminars. Those were very good from academic CV. Okay. Yeah, but I'm gonna copy down in a notepad what you wrote because I want to think more about that. Because that's the thing I've been struggling to kind of explain simply. I have kind of half an explanation, and if anyone watched me when I was on Shane's stream it like a month ago or something, I try to sell it as like a thinking about like approximations for the area under a curve, and I forget exactly how, but yeah, I'm not really in love with how I explained that. Oh, smaller than 10. That's an important thing. Okay. But actually, that's probably still helpful work to have. Um, Doppler effect is saying LCM plus 1 of those. That would make sense. Yeah. And so the LCM of these is going to be 60? Yeah. So 61. Hey, Cigar. Projectile motion? I can probably do it. So, okay, we want to... Why can't we just say m less than 7? Well, 0 less than m less than 7. This was technically correct about 1. So, like, the thing with sine is that it's bounded between 1 and minus 1. So if we multiply it by 7, it's bounded between minus 7 and 7. I still feel like I'm missing something. Because it's just 7. I don't think so, Pradyumna. If m is 9, you can go as high as 12. I but like this is just it. Like if you just know how sine works, if you want it to be at most 10, then don't put it over 7. I don't get why we need to think any harder. I'll reread the hint, see if I'm missing something, but like... I don't think I get it, Shuri. I think either the question is still incomplete, or you don't need to think as hard as that hint is saying. Doppler, I am A-okay. Empire, you can't do that in YouTube chat. You can put it in the Discord, though. Yeah, sure. I mean, I'm sorry, but it's just, like... It's just 7. Like, I feel like this kind of... I don't think there's anything more that needs to be said. Like, it just works. It's like, if I set it to be 8, our maximum is now, 11, basically. Uh... So yeah, I don't know, Sure. As far as I can tell, it's just everything that there is to the question. Okay, so it starts off with Rom having 17 less. Then Rom takes 6 away from Hari. And so that means Rom gains 6. So that am I gonna think about this right? This feels like a trick question. I think it's both Rom gains 6 and Hari loses 6. So we're going to do 17 minus 12 is 5. But this feels like a trick question. Yeah. Okay. Yeah, it sounds like we have agreement. So Guard, the trick with that question is that you have to account for Rom gaining, but also Hari losing. Uh, that's just a screenshot, Empire. What's the question? I don't know what X and Y are. Like just the position at any time? Just the displacement. Okay. So Empire wants to find X and Y, which are the position at any time. I guess we're starting at the point 0, 1. So the equations that we need here are y is equal to starting y plus starting velocity sine of theta times time minus 1/2 g times squared. Displacement when the ball lands. Okay. And then the x at any time is just initial velocity cosine theta times time plus initial x position. Hey, Lycan Dragon. I'm just a tutor. Infinvox, I'll do your question after this one. So plugging numbers in here, we get y equals 1, the starting y. And now the starting velocity is perfectly horizontal. So in the y direction, this is just 0. So I'm going to go right over to the minus 1/2 gt squared. And I'm going to say that g is 9.8 meters per second squared. And then the equation for x, the starting x is 0, and all of our velocity is horizontal, so that's 2 times time. And so if we want to know the displacement when the ball lands, if the ball is landed, that means y equals 0. So I'm going to set y equal to 0 and solve for t. So we're going to get 1 equals 1/2 times 9.8 times time squared. That's just 4.9. Then divide the 4.9 over. It's times squared, then square root each side. We're going to take the positive root. Is that 0.7? I don't think it is. Is equal to time, and that's work for our calculator. Uh, 0.45, I'll call it, in seconds. And so we know that it takes 0.45 seconds for it to hit the ground. So if we want the displacement in x, we'll take our equation for x and plug in that time. So the x that we're interested in is 2 times 0.45, which is 0.9 meters. So that's how I would do that, Empire. Your latency is weird. You had a question, Lycan? Yeah, what's up? So my setup, I noticed that for my old setup, it has been raining. Huh. Yeah, that's weird. Famished. You already saw this when we were looking for a take. You were in a test today where they gave you 60 seconds to solve this. Okay. The x is 0.678. Yeah, post the solution then. Because I don't know what I did wrong. Uh, I don't think I know how to do that. My word's worth. I'm sorry. I'll take a look at that in just a second here. This is such a long solution. Yeah, you know, this is such a weird way of I haven't seen this way of doing it. I don't know what the hell this part is here. We don't know that it goes through two, unless. So Empire, I either I'm solving a different problem than this guy, or he made a mistake when he did this step. Because this setup for a parabola doesn't make sense to me for what was written on the board. So I don't know what to say about that, besides I think we solved a different problem. Like in Dragon is saying, two trains are on the same stretch of track traveling towards each other. They are currently 120 miles apart. One train is traveling at 60 miles per hour. The other is traveling at 40 miles per hour. How long does it take the trains to collide? No calculator. Well, after 1 hour, okay, I guess you would think about it as it's the same thing as one train traveling 140 miles per hour. No. Sorry, 100 miles an hour. That makes more sense. And so it's basically how long, if you're traveling 100 miles an hour, how long does it take to travel 120 miles? So I would do 100 divided by 120 is 10 divided by 12 is 5 divided by 6, which is a repeating decimal. That I don't know off the top of my head. Wait, 5 out of 6 miles, that doesn't make sense. Did I flip it? Sorry, it's 120 over 100. I did it wrong. It's 6 over 5, so it's 1.2 hours. You looking for like my opinion on that question? I mean, it depends what the context is. I don't see anything especially wrong with that question in general. But there are some contexts where that question would be maybe a little bit mean. But yeah, Empire, I don't really, I don't know what else to say about your problem, because I think I'm missing some context about what was actually happening. Is it 60 seconds to solve reasonable, or is that over the top? I mean, it depends who you're asking. I if I didn't mess it up initially, I would have solved it in 60 seconds. I think 60 seconds to answer any question is kind of mean because it just puts a lot of pressure and people are going to make mistakes that they wouldn't normally. So I'll probably give like 2 minutes. But it's not a particularly hard question, I don't think. Like it should be able to be done quickly if someone understands that trick with thinking of it as one train. And even then, it wouldn't be that hard to calculate it with 2 trains. Because I was originally going to think after 1 hour, they've covered 100 miles. And so then you just have to figure out how long it takes them to do the remaining 20. Shooting me all day is kind of on the spot with that. Yeah, like if I was in like a job interview and they gave me that in 6 seconds, I'd feel kind of put off. Like, seriously, I need to do that in 60 seconds? If it's like a competition or something, then yeah, sure, go wild. But for a more like normal context, I don't think there's a reason you should be able to do that in 60 seconds. And like someone who can do it in 60 seconds isn't necessarily better than someone who can do it in 2 or 3 minutes. So I don't think it's, if they're trying to just like figure out intelligence or something, then that's not a very good measure. 25 of those back to back for a job, that's crazy. Like I could see a justification for that if they want someone who can work well under pressure, I guess. But if you're trying to measure intelligence with that, at least, I don't agree with that. It depends on the type of job empire, but some do, yeah. When I applied to be a tutor at a community college, they gave me a math problem. They let me sit alone in a room for like 15 minutes beforehand, though, so it wasn't unfair. Like, do you mind if I ask what type of job it was? Like in? If you'd rather not say, that's completely fine too. But I'm just kind of curious. Okay, I feel like they're leading you towards momentum, but wouldn't this be easier thought of in terms of energy? My instinct is to say that in the initial state, when A is being raised up to H, the entire energy of the system is mass gravity H. And so when it's time for C, just make sure there's no catch here. I'll say like E initial. Yeah, so I think just by conservation of energy in part 1, C would have to raise up to the same height H. I don't know what they mean by subsequent motion of the system. Like, would you just describe that in words? But C will definitely raise up to whatever same height as A does, because the collisions are elastic. Nothing's being lost to heat here. So they're just going to go back and forth forever in that state. And then for part 2, we would set mgh equal to 3 mg and then height of C. And we just want to isolate height of C. So we divide each side by 3 mg. The mg's cancel. And so we'll get h over 3 equals hc. So I would say C raises up 1/3 of the height of A. And I think that's all you need for that question. Hey, Krishu. Okay, so what was up with Fembox's question? Remainder 1 divided by 2. It's an odd number. 2 when divided by 3. 3 when divided by 4. 4 when divided by 5. Hey, Socknow. Wait. Okay, hola is Spanish. What is allo? Oi, I assume, is just a noise that doesn't belong to a particular language for hi. Allo is French. Oh, okay. Krishu, I'm not super good with electrostatics, and I'm gonna want to wrap it up soon, I think, so I'm sorry. Always Portuguese, it could also be used for Latin too. So wait, Portuguese I thought was hola, but without the H. And I think there's an accent over the O or the A. Like, I feel like every human says oi in some context. That's like a common noise. Or maybe oi is another one, I don't know. In Portuguese, but I definitely know that hola is a thing in Portuguese too. So maybe we just think about this in steps, like remainder 1 when divided by 2 means odd. You're screwing up the fish problem. There's probably an algebraic way of doing this, but I can't really figure it out immediately. Remainder of 2 when divided by 3 means like 5, 8, 12, not 15. Oh, that's because that's 11. 14, 17, 20, dot, dot, dot. Brazil, there's tons of Spanish mix. Oh, okay. That makes sense. 3 when divided by 4 is like 7, 11? No. Yes? Yeah. Yeah. Oh, but 11 won't work for the next one. Portugal and Spain, they definitely have walls with the way they speak. Yeah, I've heard from a Portuguese speaker that, or sorry, from a Portuguese speaker in Portugal that Portugal and Brazil have very different ways of speaking, in that like the Brazilian Portuguese is, it sounds almost more like a song. I think 29. No, not 29. I take that back. Oi is high. Hmm. Okay. I don't know how else to do this besides just stupidly calculating it like this. I don't think I'm getting anywhere though. Dude, I can't do arithmetic. And I'm sure there's a way you can figure this out based on the constraints here. But I'm getting like too many variables. Mathematically speaking, language is living cryptography. Ooh. That's a neat way of thinking about it. Language is how we basically encode meaning to things and communicate it. Which smallest number must add to 100 so the resulting number is completely divisible by 6? Uh, I mean, so I know that my mind immediately goes to just getting to a multiple of 6 that I know and working backwards. So I can tell immediately that 6 goes into 120. And I know that because 6 goes into 12, and you just do 12 times 10 to get 120. And now from 120, we just subtract off 6 until we get close to 100. So we can even subtract off 3 6s. So that's 18 to get to 102. So I guess the smallest number you would add is 2. So if I don't have a calculator, that's how I would figure that out. And being academically radical here. I mean, I can see an argument for that. Like, what's the actual definition of cryptography? I guess it's not necessarily secure, but it... Hmm. This is pretty specific, I guess. There's definitely context where language it, like would meet that criteria. But I'd say probably the general purpose of language is to be widely understood, which kind of flies in the face of security and the presence of adversarial behavior. But like in a way, that's kind of a funny way of thinking about it. Nope, this dark mode hurts my eyes. Can't do that one. But okay, I think I want to call it here because I'm getting kind of tired. And I want to eat food. So yeah, could be looked at as community security, like how clicks work. I mean, yes and no. The trick solution is that n plus 1 divides 2, 3, 4, 5, so n plus 1 equals 60. That's why you applied -1. N plus 1 divides 2, 3, 4, and 5. Really? Oh, I didn't even think about that. So 59 is the first kind of solution that was intended. Again, 119? No, it's 102. And so you would add 2. But yeah, we're calling it there. So I'm getting hungry. So yeah, people here on YouTube, thanks for being here. On Twitch, we'll look for a raid. Goodbye, YouTube.